People, hope we're doing well. This is video 2, continuing to go through examples of integrating using partial fractions. This one, we actually have to do a little bit of work because it's not factored. Unlike the last example in the first video, the factorization here is really not visible. But, you have a leading coefficient of 1, and 3 is prime. So if there is a linear factor in there, you basically, it's really easy. There's 4 options, x plus 1, x minus 1, x plus 3, and x minus 3. And it actually turns out to be x plus 1. So I'll spoil the surprise, and I'm not going to walk through the synthetic division that gets me there. And if but basically, if you want to practice your synthetic division, get down with your bad self, do your thing. All right. So, and the depressed quadratic that it reveals is x squared minus 2x plus 3. And of course, that doesn't factor any further. In fact, that doesn't even have any solutions. That's always positive. And if you're wondering, how do I know it's always positive just by looking at it? X squared minus 2x plus 1 is the perfect square trinomial. Think about the graph. It has 1, 0 sitting because it has a 0 of tangency. And then plus 3 is basically the perfect square trinomial moved up 2 units. So that quadratic is always positive. Alrighty, let's go ahead and, since we now have our factorization in the denominator, let's go ahead and set up. We know that we're going to have one linear and one irreducible quadratic. So we have a over x plus 1 and bx plus c over that irreducible quadratic. That irreducible quadratic means I won't be able to do much of this in terms of the Heaviside method, but I will be able to get my a value, which is going to be helpful, and then we'll move forward from there. Okay, we're going to basically let x is equal to -1, and when x is equal to -1, I'm going to get 1 plus 4 plus 7, which is 12. When x is equal to -1, this whole term right here is going to go to 0 because x plus 1 is going to go to 0. And I'm simply left with a. This becomes 1 plus 2 plus 3. So that winds up being a times 6. And of course, that gives me a is equal to 2. So with that little interlude, let's go ahead and now let's break it apart. Now remember, from here, once you're done using the Heaviside method and you've gotten all of the values that you can get that way, there's 2 ways to proceed from there. And one of those is by means of coefficient comparison, which is what I'm going to do right now. The other one is you simply, instead of plugging in those convenient values that are going to yield zeros as factors, what you do is you just start plugging in random values. Of course, not totally random. You don't want to plug in like, 117. You want to plug in relatively small numbers to make the arithmetic easier on yourself. But if you plug in just random numbers and you plug in 2 random numbers, you'll get 2 distinct equations in terms of 2 variables, and from there you would set up a system. And what we're doing right here, once we actually gather all of these things together, is sort of, system-esque, because we are using substitution and stuff like that in order to get what we need. But we're not, lining it up and, thinking about, oh gosh, should I use matrices, and not formally, looking at them. But we do recognize from here that we have certain things like b plus 2 is equal to 1, right? Because this is true for all x, it's going to be true for any particular x, and therefore the coefficients must be equal to each other. I could set the middle one equal to -4, but since this one is going to be in terms of one variable, and the constant is going to be in terms of one variable, this is just going to be b is equal to -1 and c is equal to 1. 1, 2, 3 values, yay. And so what I get here is I get 2 over x plus 1 And I could do, plus negative x plus 1, but I'm going to basically turn this plus into a minus so I can rewrite this as x minus 1. And so all I did was just basically, it was negative 1 plus x. I just factored a negative 1 and put it right here. And the reason I did that should be evident once you look at this. X minus 1 is merely a numerical factor of 2 away from being the derivative of the denominator. So I notice that I can basically change this integral, because this right here is exactly equivalent to that rational expression that was in the original integrand. I can go ahead and basically change this. And I'm putting a 1/2 out in front here because I'm going to turn this into 2x minus 2 dx over x squared minus 2x plus 3. And it just so happens that that numerator is the derivative of the denominator. I'm going to have 2 natural log absolute value x plus 1. And you don't need the absolute value for this next one because, as I've already pointed out, x squared minus 2x plus 3 is always positive. So the absolute value bars would be redundant and unnecessary. But that winds up being your derivative. That winds up being your integral. So yay us. All right, let's do another one. This problem right here is a little bit different, and we don't see many of these, but I want to occasionally throw an occasional one in there because it's important to remember that I have to basically do the decomp with a remainder expression. This, because the degree in the numerator is larger, this is the rational expression equivalent of an improper fraction. And by doing the polynomial division, I'm basically turning an improper fraction into the polynomial and rational expression equivalent of a mixed number. And that's what needs to happen. When I do the division, and let's go ahead and do it. X squared plus x minus 2. Remember the placeholder for the squared term because the numerator doesn't have a squared term. How many times does x squared go into x cubed? It goes in x times. So we have x cubed plus x squared minus 2x. Remember, I need to distribute that negative, so it's x cubed minus x cubed is 0x cubed. That was kind of the point. 0x squared minus x squared is negative x squared. Negative x plus 2x is going to be plus x plus 3. Now, from here, how many times does x squared go into negative x squared? Well, it goes in negative 1 times, and I get negative x squared minus x plus 2. And you get, of course, the first term is going to cancel out. That was kind of the point. X minus a negative x, you get 2x, and then 3 minus 2, and you get 1. So basically what happens is this winds up x minus 1 plus 2x plus 1, and then of course that denominator factors as x plus 2 and x minus 1. And basically this is the form, of course, that we need to deal with because we need to do the decomp for that remainder expression. We have two linears, so it becomes x plus 2, a over x plus 2 and b over x minus 1. We're going to go ahead and multiply through, so I get 2x plus 1 is equal to a times x minus 1 plus b x plus 2. We, of course, have linears, so that we can use our convenient values to zero out one term or the other. So let's go ahead and let x is equal to 1. And if x is equal to 1, we get 3 is equal to, and of course this term right here goes to 0 because 1 makes x minus 1 0. And I get b times 3. So b is equal to 1. Let's go ahead and let x is equal to negative 2. If x is equal to negative 2, this becomes negative 4 plus 1, or negative 3. This term right here goes bye-bye, and I'm left with a times negative 3. So we get a is equal to 1. Okay. Well, now we're getting somewhere. That original becomes x minus 1 plus 1 over x plus 2 plus 1 over x minus 1 dx. And basically, it's really straightforward, term by term. There's nothing, there's nothing weird about any of this. And that winds up being our integral. Okay. The key being that you have to do the division first, and basically deal with, you need to deal with the decomp of the remainder expression. Now this one's going to be kind of fun, because in order to decompose into partial fractions, you don't actually have to go through any of those methods, because when we get x squared plus x plus 3, we can factor that denominator into x squared plus 3 squared. Now, you're thinking to yourself, okay, well, that's a repeated non-reducible or irreducible quadratic, but I still don't see how in the world I'm going to do it without grinding out the method. Well, stop, think, then do. So if we stop and consider this, it's a fraction, right? And when we have a rational expression like this, there are only a number of things that we need to be thinking through, one of which is, okay, well, can I pull it apart? If I can pull it apart and do some canceling, then I actually wind up with x squared. I'm going to reverse the x and the 3 right here. Oh my gosh, will you look at that? That means that if I pull it apart, I'm going to get x squared plus 3 over x squared plus 3 squared plus x over x squared plus 3 squared. And all I've done is reorder the numerator and then separate the fractions strategically. Now I've done it in such a way that this is going to cancel rather nicely and is going to leave me with 1 over x squared plus 3, because this x squared plus 3 as a factor of the numerator cancels with one of these, plus x over x squared plus 3 squared. And the thing is that if you were doing it, you would basically have, ax plus b over this and cx plus d over this, and it just so happens that I've done it without making recourse to that, which is, kind of cool. And when I separate these out, you get dx over x squared plus 3. And then, of course, over here, you're going to get, let's turn this into, let's go ahead and leave it like this for right now, x squared plus 3 squared dx. Now, this right here is looking a whole lot like it needs to be transformed such that I can deal with it as arctan. This one right here, the numerator is not the derivative of the denominator, but it is close to being the derivative of what's inside. So this is just going to wind up being simple u sub with a u to the negative 2. So let's go ahead and change the form of those. Now, in order to transform this so that this is a 1, I need to factor a 3 out of that denominator. If I factor a 3 out of that denominator, I can go ahead and put it as 1/3 dx. This winds up being x squared over 3 plus 1. Now, this one, I'm not going to leave this down here. I'm going to basically rewrite it as x squared plus 3 to the negative 2 times x dx. Now, once I've done this, I recognize that if I want to turn this into a single expression that is squared, I need to basically turn 3 into root 3 squared. And if I do that, I recognize the fact that I'm going to have x over root 3 squared plus 1. Well, the derivative of that is 1 over root 3, because that would be the coefficient of x. But I have that squared in the numerator. What happens here is I need to basically separate 1/3 into 1 over root 3 times 1 over root 3, pull one of them out in front, and this winds up being u squared plus 1, and that numerator winds up being du. Now here, this is x squared plus 3 to the negative 2. I'm going to need 2x dx, and I'm going to have to pull a 1/2 out in front of here in order to do the u sub. Now, you ought to be, getting better at u sub, and to the point where sometimes you can do it without having to actually do the real substitution. You ought to be able to see, that this is 1 over root 3 du u squared plus 1. And we'll use a different variable instead of u because it's not going to be the same. This right here is, we'll call it t, right? We'll use t substitution. T to the negative 2 dt. So those, like if you can look at this and see that, you don't actually have to do the substitution to sort of make use of its logic. And this first one becomes 1 over root 3 arctan of u, and of course the u is x over root 3. Then I have t to the negative 2 becomes negative t to the negative 1. So this actually, let's do minus 1/2. And then, of course, t to the negative 1 is going to be just 1 over x squared plus 3 plus c. And this right here is your integral. Now, could I have gotten to here without seeing that cancellation? Sure, it could have gotten there just by actually doing those, like grinding out some of the methods that we've talked about in terms of decomposition into partial fractions. But how much easier was it once we recognized that we could reorder the numerator, because addition is commutative, and then we could unsimplify that single rational expression by separating the fractions. And of course, we'd picked our terms strategically such that one of them reduced, and we got to here. And the decomp, and I went ahead and did the decomp just to see how complicated it was going to be. It doesn't wind up being all that bad, because it basically it winds up being really, really straightforward, and you get, two of the values wind up being 0, right? Because this is not a linear up here, and this linear doesn't have a constant term. But go ahead and work out the decomp if you're curious about it. And if you have any questions, obviously, ask me. Let's go ahead and do another one. This one, again, is going to require factorization of the denominator. But this factorization should be really, really straightforward, right? It should be, this winds up being, this is a difference of 2 squares, and when we do it, you get the difference of 2 squares again, because you get x squared plus 1 and then x squared minus 1. Well, x squared minus 1 further factors into x plus 1 and x minus 1. So we have 2 linears and 1 irreducible quadratic. I usually put my irreducible quadratics at the end, despite the fact that this factor is right here. So let's, and it doesn't really matter, but I think it's probably an aesthetic thing, or just maybe it's just habit. But that winds up being, if we need it to be, it can be ax plus b over this, and then c over x plus 1 and d over x minus 1. It doesn't really matter. But let's go ahead and multiply through by those denominators in order to arrive at our polynomial version of this equation. And we get cx plus d, and I'm going to go ahead and write the x plus 1 and x minus 1 as x squared minus 1, just remember that that's what constitutes it. Now, because I have an irreducible quadratic, I should note that I'm not going to be able to use the Heaviside method in order to get rid of everything. But I will be able to do it to get rid of, to basically find a couple of things. So let's let x is equal to 1. And when x is equal to 1, the a term and this cx plus d term go to 0 because they both have a factor of x minus 1. And the only thing that's left is our b term, and I'm going to get b times 2 times 2, so b is equal to 1. Let's also let x equal to -1 to take advantage of our x plus 1 factor. Now, x plus 1 is in this term and this term, so basically those are going to disappear, and what we're going to get is we're going to get a, because it does not disappear, and a is equal to -1. Now, let's go ahead and rewrite this equation with our a and our b value. We have 4 is equal to negative, and let's go ahead and multiply this out. X cubed plus x minus x squared minus 1, and I'm doing it in that order for a specific reason. And I get x cubed plus x squared plus 1. And this right here becomes cx cubed plus dx squared minus cx minus d. Now when I distribute this negative right here, I'm going to get negative x cubed minus x plus x squared plus 1 plus x cubed plus x squared plus 1. And of course this remains unchanged down here. This right here, these are both negative, these are both positive, those terms cancel out. And I'm left with, and if I'm looking for the cx, I have a second degree, a third degree, a second degree, and a first degree, and the rest are constants. So this becomes cx cubed plus d plus 2, right, because I have dx squared, and x squared. And then the only linear that's left is this right over here, and I'm just going to call it a negative cx. And then I have 2 minus d. Now remember, this is just 4 over here, so it's understood to be 0x cubed. So c is obviously equal to 0. It's also 0x squared, so d plus 2 must be equal to 0, or d is equal to -2. And all of a sudden, really quickly, now this coefficient comparison wound up being really, really clean, right? And so what we need to do from here is, let's go ahead and set up our integral. A over x plus 1. Well, as we know, a is -1, so we get -1 over x plus 1. Okay, b over x minus 1. b was just 1 over x minus 1. And then c, so there's no linear term because my c value is 0. And d is equal to -2. I just get -2 over x squared plus 1 dx. Well, this doesn't wind up being too difficult. And if you want to split it apart into its separate integrals, it would look something like this. But whether you do that or not, it's still negative natural log x plus 1 plus the natural log of x minus 1 minus 2 arctan of x plus c. And there we go. Okay, now we're going to get in the next video and the ones that follow. I'm not exactly sure how many more videos we're going to do. We're going to get into ones that are a little bit more complicated and might with regularity spill onto a second page. But I need you to go ahead and shoot me an email if you have any questions on this. Yeah, bye.